So page 52 is talking about what happens for momentum problems when the mass of an object is changing. Not on the test, but if you guys are interested in that, it's basically rocket science. Sorry about that. So 9.49 is really interesting, not on the test. If you're curious about how rockets work and how you do the calculus for when the mass is changing, there it is. If you're a physicist, someday you may actually have to use what's called the center of mass frame. That's on page 53. Also, not on the test. But if you're a physicist, you might want to skim over that. Just thought I'd mention that. I didn't say that at the end of last lecture. We now want to move on, basically just clarifying 9.49 and basically page 53 are not on the test, but they're useful to some majors. I want to look at page 55, rotation. In particular, rotational kinematics. All right, and now it's probably going to take us most of the day here to get through this all, but well, let's just start. You've got a lot of stuff written on that page, on page 55. And I want to start by saying theta is going to be called angular position. So you remember in chapter 2, we had x was a vector and x was the position, not the distance, not the displacement. And we had delta theta was angular displacement. Well, maybe we'll have angular velocity. Does anybody happen to recall what variable that was, what letter it was? Looked kind of like a W. Omega. Omega. So it's not a W, it's an omega. And then we might also have angular acceleration. That's going to be fish swimming left, or alpha. And the first thing I probably should say, well, let's put the units on these, right? What are the units of an angle or an angular position? What do you think? Radians, because we're going to have to do calculus at some point. So you might think it's degrees, but it turns out we're going to want to use radians. And that's going to be the same for angular displacement. So angular velocity would be radians per second, which is a lot like RPMs. So people usually think in degrees, but we write radians. We usually think in RPMs, but we're going to use radians per second. Okay? Angular acceleration would then be radians per what? What's in the denominator for accelerations?
Second squared.
Second squared. All right. I'll mention a couple other things here. Period. That's time to complete one revolution. And frequency I'm just going to write it as 1 divided by the period. We should get the units. The period is time to complete. What are the units? Time, seconds. This in units of 1/seconds. That's hertz. So hertz and 1/seconds are the same. All right. I'll write out the word here. The German word for heart is H-E-R-Z. If that helps you kind of remember 1 per second, it's kind of like your heartbeat. I don't know, maybe that helps, maybe not. Okay. Now, I need to be very careful here. We've got all the units, we've got all the symbols. They are not actually vectors. We're going to treat them like vectors if we restrict ourselves in one special way. Okay. So and this is the note, this is written there. Do you see this note on your page? Strictly speaking, theta is not a true vector. I'm just going to summarize that here. We are going to restrict ourselves to rotation about a single axis. And you may be saying, oh, well, that's not much of a restriction. But in some cases, you might actually be rotating about the x-axis and the y-axis simultaneously in a spaceship or something. Basically, as long as we're rotating about a single axis and that axis isn't changing, then we can treat these things as vectors. Okay with that? It's subtle. It comes from the fact that if you rotate about the x-axis and then the y-axis and then the z-axis, the final orientation of the object is different than if you do z, then y, then x. The order of the operations matters for rotations. And I could prove this to you after class if you want. We could take a book or like if you rotate it. Anyway, enough said. Okay. Basically, vectors, the order shouldn't matter. And it turns out for rotations, the order in which you rotate does matter. Therefore, they're not true vectors. Only in this special case. All right. Let me give you another comment here. Let's go back to chapter 2. Somebody probably knows an equation from translational kinematics. By that, I mean, does anybody remember any of those equations we used in chapter 2 for constant acceleration? So, yeah, any of those equations. Yeah, like V final, right? V final was equal to plus AT. Or maybe you had delta X was equal to V initial T plus 1/2 AT squared. Do you remember that one? What was the last one of the big three? Wasn't it V final squared? Yeah. Well, it turns out we can actually do constant acceleration rotational kinematics. And now let's take a look. The trick, these equations are written on your exam equation sheet somewhere, I forget where. But the idea is you need to know this step. We need to know how to know the definitions of these variables and rewrite the x equations in terms of thetas and such. Well, what is the rotational equivalent of velocity? Which symbol? Theta, omega, or alpha? Omega, because it's angular velocity. You agree? So how do you think I might rewrite this equation? Instead of V final, I might write omega final equals, what's the rotational equivalent of A? Alpha T. Does that make sense? What do you think would be true for this one then? Instead of delta X, what do you think I would write? delta theta equals omega initial t plus 1/2 alpha t squared. Are you starting to see a pattern here a little bit? Anywhere we had rotational or translational kinematics, we could just replace the variables with the equivalent rotational variables as long as we're only rotating about a single axis. And let's finish this out. This should all be on your handout. Okay. And here, I just want to point out, remember on all of these, there was an I hat implied on V, A, and delta X. Do you remember that? There was a hidden I hat on all of those quantities. Similarly, plus or minus direction implied on omega, alpha, and delta theta. So we'll basically, quantities in here could be plus or minus, quantities in here could be plus or minus. You could be speeding up, slowing down, you could have positive omega, negative omega. I'll explain a little bit more about the direction in just a second. But so far, how are people feeling on this? This is all on page 55. So remember, all day today, if you forget some of this crap, just look at page 55. All right? Let's do a couple more things here. All right? What if it's not constant? You remember some of the stuff that we had to do in chapter 2 when acceleration wasn't constant? What's that? Split into stages. Excellent. We could split this into stages and do constant acceleration on each one. What's another thing that we sometimes did? We could do separation of variables. And for example, if alpha depends on omega, or if omega depends on theta, that would be a case when we might do that. If they depend on time, what's another thing that we could do? Without having to separate, we could also, I'll just tell you, take derivatives and integrals just with dt. Remember that? So if we didn't have to separate, you could have alpha is equal to do you remember when we just do the integral? You can take the derivative of omega to get alpha. If we integrate alpha, what do we get? You flip this over and then you integrate both sides, what should you get? Not quite. It was change in omega. Remember that? The area under the curve was not omega, but the change in omega. Did that, or the area under a VT curve was the change in X. It wasn't X. Do you remember that from chapter 2? Or the area under the AT graph was the change in velocity. But whatever, there's a change in there because you'd have to go from you'd integrate this and you'd have an omega initial to omega final. Okay. Similarly, we could do something like this. Do you remember that? Basically, we could take derivatives or integrate of your velocities or accelerations. This probably you might want to write on the page because I don't think I could fit it in there. So you may want to write this crap down. Okay. And now I want to focus on the direction here. Okay. Give ourselves some space here. Okay. Anytime you write down a coordinate system, we should always check if it's right-handed. What do I mean by that? Does X go to Y, go to Z? So in this case, what direction is the Z axis if this is X and this is Y? Let's remind ourselves of the wheel of pain. I goes to J goes to K. Get your right hand out. Just do it. Who cares how dumb you look? I goes to J goes to K. Which way is the Z axis? Out of the page, towards you, however you want to say it. By the way, it looks like 4184 is the number, but that's at 15C. I don't know why.
Oh, I see. Okay.
Yeah, anyway, we were talking about that. So I'm not sure if physicists are doing it at 0 or what.
That's really weird.
But yeah, 15C is closer to room temp, which makes more sense to use 4184. We were looking at some constants, and I've seen it two ways in two books, and we were talking about this the other day. Doesn't matter.
Now,
All right.
when you were drawing that, like it took a lot of strength for me to not yell out right hand rule.
Yeah, right?
Right.
You use it a lot.
Yeah.
Even chemists use it. So anybody can. Oh,
That's not fair. I almost double majored in physics. So
Okay.
That's why.
that's why you're weird.
Yeah.
Okay, okay. Later, man.
Physics more than I should.
Yeah, yeah. All right. Let's say we have our ball on a string here or something like that, right? Or rod rotating. I think most of you would have no trouble saying that's the radius of the circular motion. Most of us, the default, do you agree the default in a math class is to measure angles from the x-axis, right? So let's say that this is theta. You could say it's delta theta. In this problem, let's say theta initial equals 0. Therefore, delta theta is equal to theta final minus 0. So let's just say delta theta is just theta. Is everybody okay with that? A lot of times, as long as the initial angle is 0, we don't need to write delta theta, delta theta. We could just write theta. Am I losing you or is this okay? Okay. What's a good name for this dotted line? Arc length. What's the letter for that in math class? S. Does anybody know how S, R, and theta relate from the lab we did the other day? S is not your theta, it's R theta. That's so dumb. S is R theta. Is everybody okay with that? What units have to be used? Do a unit check. What are the units of arc length? Arc length has units of length Meters. Radius has units of meters. So what does theta have to have? Unitless, which is radians. That's why you're always using radians in a calc class, because then the units work out. So far, so good? Now let's say it's rotating this way. So it's rotating that direction. Okay? Do you agree it would be moving this way, V? And sometimes this is a velocity. Do you agree that this is tangent to the circle? Sometimes people call this V subscript tan, meaning the speed tangent to the circle. How do you think the speed relates to the omega? How could I get omega from this equation? Derivative. If you take a derivative each side, what's the derivative of this? Meters per second. If the radius is not changing, that's a constant, we get that's just a derivative of that. Does that make sense? Right? If you take the derivative of the arc length formula, you'd better get a speed or a velocity vector, right? Well, taking the derivative, if the radius is constant, then it just pops right out. G. How do you think you get the tangential acceleration? Follow the pattern. Take a derivative, omega changes to alpha. Okay. Now let's think about the directions of these carefully, right? That's our goal, is we're trying to figure out the direction of these quantities. V tan, that's pretty easy. It's tangent to the circle. However, what is the direction of omega? Get out your right hand and curl it in the direction of omega. Which way is my thumb pointing? I hat, J hat, or K hat? Which way is my thumb pointing? K hat. So we would say that omega vector is equal to omega in the K hat. This is written down for you on the page. Look at this carefully. You guys see that midway down? How do you find the direction of angular quantities? Notice your thumb is lining up with the axis of rotation. The direction is even though this seems kind of weird, remember, these are not really vectors anyways. Right? It's not a true vector because we can't do addition correctly. But in this case, we can treat it like a vector if the only axis of rotation is z. So if something's rotating about the z-axis, this would be positive k hat, this would be negative k hat. So instead of saying clockwise, or whoops, instead of saying counterclockwise and clockwise, we would say k hat, negative k hat.
So if we could somehow draw it like rotating towards us, that would mean it would be rotating on the x.
C, with the y-axis, right? So like if I line up my thumb with the y-axis, then it would rotate like this. Got it? So that would be rotating that way. And then, oh man, even that made me dizzy. But like if it was rotating here, it would be, oh, I see what you're saying. Yeah, it would rotate in the x-axis too. So it'd be coming out this way and then under. Yep. So yeah, you could, is that good?
Yeah.
And that's just, and if you're coding, This is how you do rotations in coding. Alan's been doing it nonstop for like 5 weeks, nonstop. So, yeah, good on that? All right. Now, wait a minute. Let's just finish this out because we're so close. We're talking about atangential. Do you guys know any other acceleration vectors for circular motion? AC. What's your equation for AC? Do you remember?
V squared over R.
V squared over R is a good one. What was the other one I told you that we sometimes use that relates to omega?
Omega squared.
R. So notice this is convenient when we're doing angular quantities. If you know something's RPMs, you can get AC. Well, wait a minute. In this case, let me see if I can draw this really quick. This would be A tan or AC if it's going this way. A tan, good. That's a squeaky marker. There's AC. What if I just wanted the acceleration? Sometimes we call that a total. I call it a tot for a total. Now keep in mind these, do you agree these are not vectors here? These are just some numbers. So in this case, I could get the magnitude of a total by how would they relate to these two numbers? If I wanted to get the total acceleration magnitude from these two vectors,
Square root.
yes, nice. Man, you're on fire today. Take the square root, we add them in quadrature, meaning square them, basically Pythagorean theorem, right? You got some amount this way, some amount that way. You can make a triangle out of them. Sorry, this is such a squeaky marker. I'm getting through it. Jeez, that's annoying. But does that picture kind of help? We just say AC squared plus A tan squared equals A total squared and then square root it. Good? See if I get it less squeaky red. It's just going to be squeaky. All right, whatever. We'll deal with it. All right. So far, so good. Let's see if there's anything else I wanted to say about this. Oh, look at the stuff at the bottom. There's a relationship relating translation to rotation, and maybe I should draw this here. Need a little more space. Give me just a second. This kind of foreshadows something, right? I know this is going to seem a little bit strange, but I'm going to write the kinematics equations 3 times. Okay? In horizontal kinematics, we've been saying something like delta x equals v initial x times time plus 1/2 a sub x t squared, right? In rotational kinematics, I was telling you we could change this to delta theta, right? Delta theta equals omega initial times time plus 1/2 alpha t squared. And just like we usually set x initial to 0 and this just becomes x, we can often set theta initial to 0 and just make this theta. Remember that? So I want to show you one more. I'm just going to call these arc length kinematics. The idea is we could talk about the angular quantities, but we could also talk about this axis, so to speak, around the circle, the arc length kinematics. Now check this out, everybody. What if I multiply this term and this term and this term by r? R times delta theta is arc length. S. If we multiply everything in this equation by r, this first term would become arc length. What's r times omega? And r alpha? Now it seems a bit circular, but the kinematics equations, we can take them from 1D into angular and then go into arc length. So we can talk about things moving around in circles, and we can talk about the meters, right? To be clear, I want to talk about the units here. This has units of meters, meters per second times seconds, meters per second squared times second squared. Or we could go up here and look at it like this. This is talking about radians. This is radians per second times seconds. And this is radians per second squared times second squared. And then up here, it's the same meters per second. So far, so good? Well, our goal is to do some practice problems with these now until we want to puke, and then hopefully call it a day. You should know how to do all this, except there's a lot of subtleties with the units, and if in doubt, we always want to use radians, because if we use radians, then we can use these equations. These require units of radians, not degrees, not revolutions. Just get in the habit of always using radians, even if you're not sure. Cool? Okay. Ready for a practice problem? All day today, remember this page 55. So if I ask you a question, flip to page 55. And like you could be like, oh, that was this. That was this. Let's do 10.1 on page 56. I'm going to erase the board and get to it. I had a funny idea today. You guys probably would not like it. I was imagining, what if I just stopped repeating my lectures in the morning and the night and just started getting them all done as fast as possible. And then record them all and just say, oh, watch the video. Wouldn't that be horrible? I don't know. Maybe you would like it. I don't know. I want to get these damn videos done. Still erasing here. Alan, before we get cruising on this, any advice you have for the class on dealing with me in chapter 10 and rotation? Anything that jumps out in your mind, or was it?
Well, the thing that's mostly important is kind of related because this is all going to be the same stuff, or like the translational part, which is like the first half of the class. So I guess finding the equivalent between rotational equations and translational can help you out.
Being really good, basically having the equivalency memorized.
Yeah, because the process is all the same. It's just the rotational equivalent.
If it helps, maybe I'll mention this since Alan made that comment. Could you guys just briefly turn to page 58? There's the cheat sheet for the equivalency. Do you see it there? Translational and rotational. I was going to finish the class with that as like a summary, but so if you get stuck, just know that that's there, page 58. All right, let's go back and do 10.1. Thanks, Alan. All right. Okay, we've got a record player. Most of you probably don't use records. But imagine we've got basically a thin disk, and there's an axis. Let's call this the z-axis. So it goes x goes to y goes to z. It looks pretty good. And this thing is rotating. Okay, and says it's rotating at 33 1/3 RPMs. What symbol is that? 33 1/3 RPMs. That's omega. What does RPM mean? Yeah, rotations or revolutions per minute. What's the first thing I should do before I get ahead of myself? Convert, because we do not want to use revolutions a minute in general. So what's the conversion factor? 1 revolution in radians. What is it? Yep, 1 rev, 2 pi radian. One minute, 60 seconds. Do a quick check before you punch it in. Trust me on this, please. 2 pi is approximately 6. 60, that's don't need to have any approximate. What's 6 over 60 approximately? 1/10. Do you agree it should be about 3? Remember that conversion. It's basically either going to be, if we're going from RPMs to radians per second, it's about a factor of 10. If we're going the other way, or it's, yeah, divide by 10, going the other way would be multiply by 10-ish. Approximately. Help me out. What is that number? Punch it in. I'm going to say it's 3.4906. See if you get that. I'm going to assume it's only valid to 3. What else do we got here? Let's stick 4 sig figs on it. I'm not really going to care that much about sig figs, but let's try and do it right, I guess. If the first digit's a 1, we should use 4. Okay, great. Well, to get the magnitude of angular acceleration, how would you approach this? What did we always do in chapter 2? All right, give me some crap here. What are the things? So we used to do delta x, v initial, v final, a, and t. This time we should write what? What's the equivalent of delta x? Delta theta, v becomes
Omega.
initial, and then omega final, a becomes alpha, t. Piece of cake, right? What's omega initial? It's initially rotating at what? Yeah. Does that make sense? What's the final, Alonzo? That's the 0, right? And then, geez, it's important to put our units on. Do I know delta theta? Does it tell me how many radians or how many revolutions it completed? Does it say how much angle it did anywhere? I don't see it. What's alpha? Do we know that? I don't see anything with the radians per second squared. Time, oh, we do know that. All right. What's next? What do we do next?
Use the
Kinematics equations, okay. In this case, we're looking for what parameter? What are we trying to find? What symbol is that? Alpha, fish swimming left. Okay, so give me the equation you think will work best.
final.
You got it. You remember that kinematics equation, the V final equation? Is this about the right pace, or is this too fast or too slow, or about right? Okay, okay. I'm going to solve this algebraically before I plug in numbers just to save myself a lot of headaches. Do you agree we're looking for alpha, which should be, we plug in some numbers and we got it? It's basically divide omega by 10. Do you agree? Oh, wait, there's a negative sign here. All right. Wait, what did I screw up? The units, what should it be? Instead of seconds, it should be seconds squared. Excellent, nice. Good job. All right, what do you think? Are we ready for the next part? I'm going to rephrase. Why is that wrong?
What's the magnitude?
Yes, I said magnitude. Oh, I'm a ruthless person, aren't I? Magnitude should always be positive. Do you agree? In particular, what unit vector is implied on this answer? We're rotating, in this case, what direction? K hat. Do you agree? the magnitude would be positive 0.349. Everybody okay with that? Subtlety, nice job. It's sort of like when I asked about speed versus velocity in chapter 2, you kind of always have to think about, did I ask for A or did I ask for the magnitude of A? It's the same boring crap. I was talking with Dom earlier. He's like, all the time this shows up. Okay, got to watch for it in engineering classes too. Okay, B. The next part says I want the total acceleration magnitude 2 seconds before it gets to rest. What am I asking there with that goofy sentence? What are we looking for? A tot or a total. What was the equation we had for that? Do you remember? A tan plus AC squared. Good. Doesn't matter which order you do it in. Well, what was AC? What was the equation that relates to RPMs, basically? Not V squared over R, but so notice it's R squared omega to the 4th in there. And what was A tan? R alpha. Oh, wait a minute. I got to read carefully. It said specifically point on the rim. Why is that important? If we know we're on the rim of the record, what information does that tell us? If we're a point on the rim of the record, we know the radius. That's what tells us R equals 24 centimeters or 0.24 meters. That's right. If we don't know where we're located, we don't know what number to plug in for R. Okay. All right. What time should I use? 8 seconds, not 2, because it's 2 seconds before it comes to rest. How could I get omega? At 8 seconds. That's kind of a sloppy letter T. If I know the time and I want to get omega, what could I do? What equation might work? The one we just used. And now what's different about it is now we know the time and the alpha and the initial, but we don't know omega final. So I would say omega at 8 seconds. We know alpha, T, omega initial, we plug them all in. In this case, I'll say one last thing here. You should be using the unrounded result for alpha in here so that you don't introduce intermediate rounding. Again, you should use the unrounded value in the equation so that you don't round too soon. And then do you agree we know this stuff already? We know R, we know alpha, we got this. In theory, we could get omega. This is a trivial problem. It's just identifying the names and the labels and the equations correctly. So it's crucial to understand the definitions here. I would like to skip to part C and not do this since you've got the solutions with the answers already. Is that okay? Or do you guys want to see it worked out? What do you think? The trade-off is this. If we do every single step, I can't set up all the different types of problems. There's just no way to get through it all. If we skip a few steps that like, I'm going to try and set up as many as possible. And then if we do that, hopefully we can get through all the variations that might be on a test. Is that okay? So do the math at home, plug it in, part C. Okay, so at there, the problem is doable. Total distance traveled. I want the total distance traveled by a point on the rim as it comes to rest. What am I looking for when I say total distance traveled? What variable does that mean? Total distance traveled. You're a point on the rim. What would be a good name for the distance traveled? Theta would be angular distance traveled. So that's related, but not right. What do you think it might be then? S, arc length. Which is related to delta theta by the radius. So basically you were off by a conversion factor of the radius. Not bad. Well, how could I get delta theta? I have no idea. Any suggestions? How might we get delta theta? Right? Because I know the radius, I'm looking for S, but I don't know delta theta. How could I get delta theta? Some equation. What does delta theta equal for that equation? You remember?
Omega initial.
I got it from there. You got it. That one. Remember that? We know the time. We know the omega initial. We know the alpha trivial. Agreed? Just checking. What time should you plug in? 0 seconds, 2 seconds, 8 seconds, or 10 seconds? What time should we be using in this equation? 10, because it's for the entire time as it comes to rest. So that's a sign that t equals 10. Who cares about sig figs? What units are crucial? What units do we have to use? If we want to use this equation, this has to be in revolutions, radians, or degrees. If in doubt, use radians. Okay, this equation only makes sense if we use radians. You know the circumference is 2 pi r. 2 pi is radians. So that circumference equation is just like this with 2 pi with theta. I say we're done with that one. You feeling okay on that? Should we try another one and then take a break? Let's try 10.2. Hey, does anybody know where Kaohsiung is? It's Taiwan, southern Taiwan. I lived in Kaohsiung for a semester. It was cool. And so Sandu shopping district was a real train stop, so was Central. There's a funny thing in this problem though. I'll show you in just a minute. I was over there working on this workbook every day. Wait, was it from Central to San Duo? Whoops. And as I was riding the train, I was thinking, oh my gosh, this would be a perfect problem for my workbook. So these are real train stations. You can take them. In this case, thought you might see, how does this relate to the real world? Okay. I'm riding around on this train. I looked up some numbers. It turns out the largest rate at which you want a train to speed up is at about 1.40 meters per second squared. Right? I guess any faster than that, some people start to get nauseous. So at least this is what I read on one website. That doesn't mean it's true, but let's take that as a reference, right? So, right, that's about G over 7 for reference, right? 1/7 of G. Does anybody know how fast this is in miles per hour? You remember the conversion from meters per second to miles per hour? Just super approximate. The other way, 2. So it's about 50, 60 miles per hour. It's a little bit more than 2. It's about 2.2. So let's just say this is about 55, 60 miles an hour. Pretty realistic numbers here, okay? And that's going to finish the turn at constant speed. And we got 200 meters, 3 sig figs on that. So this one, we got all 3 sig figs. Okay, help me understand what parameters I gave you. What the heck is this? We've got 4 different accelerations, right? There's a tan, AC, a total, and then there's angular acceleration. Which one is this? Do you know? Which one is this? The rate at which you speed up. A tan. That was, we talked about this in chapter 6. So if you don't remember, don't beat yourself up. That's why we're doing this. The rate at which something changes speed is a tangential for circular motion. That's the rate of change for circular motion. Okay? It's going to reach some speed. What is this symbol? 25.7 equals what? Is it omega? Not omega, it's not radians per second. So it must be V tan. Okay. What are we looking for in part A? We're looking for the angle when it hits constant speed. Any ideas how we might approach this? What do you think? Well, let's start with what we're given. Is acceleration a constant? What do you recommend? What did you recommend earlier? You remember? Oh, you said split it into pieces. Remember that? You said just do a 2-stage problem, right? Here's a 2-stage problem. Well, so acceleration is constant for the first stage. So now, do you think I want to write this down in terms of x, theta, or s? Do I want to talk about arc length, angle or X, horizontal motion? What do you think? Arc length. So I'm going to write down the kinematics equations. S equals there's my three kinematics equations. How does this help us find the angle? I claim that was a good idea, but I don't know if you see why yet. So I'm curious if you could tell me why this is a good idea. What's something we could figure out? Maybe we could check the knowns and unknowns. You know what I'm saying? I know A tan. I know the V tan initial. Oh, wait, no, wait. What do I know? Is this V tan initial or V tan final? That's V tan final. What's V tan initial? Did it tell us? Did the train start from rest? Yes, starting from rest. That's convenient because it would be very hard to board a subway train while it's moving. Agreed? Starts from rest. Forgot to write that down. Did anybody happen to see, I don't know why this made me think of this, Train to Busan, or Busan, the Korean zombie movie? I think there's some train station where they never stop because the zombies are attacked. So there might be a reason to not board the train while it's in motion. Anyways, I'm having fun here. 0, 0, 0. Which equations are looking pretty good here? Do you know the arc length traveled? Do I know what S is? No, but I could figure it out maybe. Oh, I don't know time either. So I could figure out time from this one. I could figure out arc length from that one. Which is the way to go? What's our goal? We're looking for an angle. Which kinematics equation would you grab? 1, 2, or 3 on this board? 3, why? How do you solve? Okay, so we can get S. Then what? What do we do with it? What's the equation we could use to get from S to theta? Yeah, you can look it up. That one. Right? You had the right idea. We could get S from this equation. Once I know that, I could just basically, theta is just S over R. So we can basically convert between arc length and angle with the radius. So think of the radius as converting between arc length and angle. Knowing the arc length is the same as knowing the angle. That's part A. Part B, times. Okay. That's a two-stage problem. Part B. Let's sketch this out. Do you agree we could use that double star equation to get time? I could use this equation to figure out the time. After that, that tells me the time at which the two stages split. Right? We could use delta theta equals omega initial t and to be clear, this is stage one, the first part of the rotation, and this is the second one, stage two. The idea here is we could say, okay, I can figure out the time for stage one. Afterwards, I could figure out the angle for stage two or the arc length. And maybe this would be easier. Actually, I do like this one a little bit easier. In this case, do you agree we should, in theory, be able to figure out the amount of arc length left in stage two? If we know the arc length for stage one, we should be able to get the arc length remaining for stage two. Do you agree with that? So in theory, we could figure out this arc length for stage two. Do we know V tan initial for stage two? Maybe I'll color this stage blue here. For stage two, what is the initial tangential velocity? The final from stage one. So this one would be 25.7 meters per second. What is a tangential for stage two? 0. How do you know that? What is the words that helps you? Constant speed tells me a tan for stage two is 0. You could get the time to finish the race, and you could get the angle to finish the race. You could do whatever you need to do. Agreed? And so this was what you were saying earlier, split it into two problems, two stages. Good? All right. Oh my gosh. Once we know all this, you could actually sketch the plots. All right. And now I encourage you to at least read those and see if you, right, you're going to probably be too lazy to sketch them. That's what students, they don't like making plots. But you could try to just take a guess. Don't spend a lot of time on part C at home, okay? I want to talk about part D, okay? Part D. And maybe what we'll do is we'll look at them at the end of class or something, but I'm going to leave part C for you to do at home. We just can't do everything. Let me do this really quick. Oops. D says force on a rider. If you want to get the force on somebody riding the train, how would you figure that out? Force. I haven't talked about force. What does force relate to? In general, F equals MA, not MAC, MA in general, right? And this is what I wanted you to watch out for. Now, Alonzo was saying it's usually MAC, but in that case, we have to worry about tangential acceleration too, because now we're actually allowing the speed to change, so A tan is not 0. So instead of using AC, what acceleration should we use? A total. Well, we know how to get A total, don't we? And what did it say? It said the maximum force, is that right? What did it say in part D? Maximum? Where is the acceleration going to be maximum? For example, at the beginning, what is the acceleration right now at the very beginning? How much centripetal do you have at the very beginning? What is your speed at the beginning? 0. So what's AC equal V squared over R at the beginning? 0. After you start moving, do you agree AC is going to grow in size? When will you have the largest AC? When does AC get as big as possible?
Stage 1, 2.
All of stage 2. AC, because there, your speed is maximized right here. So from this instant, the end of stage 1 till the end of the problem, AC is as big as possible. What happens to A tangential in stage 2? 0. At what instant in time will the rider feel the most force? You guys are tired. We need that break, don't we?
Around stage 1.
Right at the end of stage 1. A tan is still there and AC is as big as possible. So what you do here, let's get out of this problem. Let's get to break. Okay. You could get a total at the end of stage 1. Okay. Plug it in, piece of cake. I love part E. Contemplate. I'm just going to walk through this with you really quick. I find this interesting, and maybe I'll get it all on a screen here real quick. Then we'll take a break, I swear. I apologize. My tennis ball on the string got taken, so we'll just do it like this. Hopefully you can see this thing. Right? So here's what's crazy. When you accelerate, the ball is going to appear to move backwards relative to you, right? But when you have AC, you're accelerating towards the center, the ball will go outwards relative to you. So what's happening is, as you speed up, right, first the ball goes straight back, and then it starts drifting outwards. And then the last half of the ride, it's just straight out to the side. Did that make any sense? You start out, it's straight back because AC is 0. As AC grows, the ball drifts out at some weird angle. And then when the tangential acceleration turns off, the fictitious force is straight outwards. Take a break. Whew, that was intense. Alan, can you see the screen kind of okay from where you are? Can you like read it, or
Yeah.
is the font too small? How about you guys over here? Can you see, or is there bad glare? Or how about on Zoom? Can you guys see okay? The screen share? Those of you on Zoom, can you see all right?
Yeah, we can see it fine.
Right on, thanks. What do you think of the Zoom lectures? Is it good enough, Isaac?
Yeah, I think they're pretty good.
All
I
right.
don't want to say names, but I've seen worse.
Yeah, right. It's like it's maybe not the greatest, but it's good enough that you can get most of it. Hopefully, most of the time I'm on the right whiteboard, right?
Yeah, I like going in person, but sometimes I don't feel like driving to SM. So
Yeah. Yeah, if it's good enough, that's great. Okay, that's cool. All right, let's go ahead and start looking at some stuff. So you guys can kind of zone out and just watch the pretty pictures for a minute, but maybe we'll learn a little bit here. So I'm just gonna run this one and then we can dig in. So when you look at this thing, notice there's a blue sphere. You can kind of see it right there. The blue sphere in the code I'm gonna call a bug. And so what I'm gonna do is I'm gonna rerun this program and I'll just show you right here. It's basically pretend that is a bug, and let's change the bug's radius to say 0.4 and watch what this does to the code here. It's closer in. Do you see that? It's a little closer to the center. And if we go even closer, we're very close to the center now, right? And so what we're seeing here is we can change the location of the bug and analyze different properties of the motion. Now, right here, let me run this again. Let's run this for a little bit longer. Oh, what's T max? Did I label it up here? Oh, jeez, where's T max? Oh, there it is. Let's say 3.7. How about just 4 seconds? So I'm going to run this thing again. And I want you to think, what are the different colored arrows that you see? In particular, what do you think the blue arrow, the red arrow, and the pink arrow represent? So at this moment, what do you think that red arrow represents? Which way is it pointing? Towards the center. What do you think it is if it's pointing towards the center? AC. So that's the AC. So then the question becomes, you've got a blue arrow and like a pink arrow. What do you think those are? Let's run the code again and watch it. AC is the red arrow. What do you think the blue arrow is? Velocity. What do you think the pink arrow is? V10, because it's tangent. Excellent. So if that helps, you can kind of visualize this. I don't know if this is helping you see. A tan is going to be, it started out opposite the velocity, then with it, and that's why it's speeding up when they're pointing the same direction, slowing down when they're pointing the opposite. So to be clear, this was V10. So let's run this one more time and watch the speeding up and slowing down. In particular, watch the directions of the arrows for A10 and V10. Right, so let's clear that crap out, run it one more time. Notice it's slowing down when A10 points opposite V. It's speeding up when they point the same direction. So far, so good? So if you're curious, what does this look like in the code? I find this, so notice I chose a theta initial that's not 0. So my delta theta would be whatever. I immediately convert it to radians. Omega is a scalar here, and alpha is a scalar here. And what I'm going to do is I'm going to specify the rotation axis. So notice if you want to code stuff, you immediately have to do the vector notation. So omega, the vector, is going to be omega times the rotation axis. Notice it's in the, what direction is that? I hat, J hat, or K hat? K hat. 1 in the Z is K hat, right? And so these are just boring. Pivot, that's just something at the center. This is just setting the time. The rod is just the cylinder I drew. The bug is the little ball, whatever. So notice the omega vector is omega times the rotation axis. The alpha vector is similar. This R vector, it goes from what to what? I'll give you a hint. It's always final minus initial. So where does it start? At the pivot, and it goes to the bug's position. Now, you might be saying, how am I going to get the velocity in the tape? Look at these crazy looking things here. Look at that. I start doing cross products to figure this out because the rotation axis is perpendicular to the direction of V. You have to do a cross product. Cross product picks off something perpendicular. So I just did trial and error. I wasn't sure if it should be omega cross R or R cross omega. So I just tried both and see which one works. Notice this term right here is actually a scalar. That's bad coding on my part, but I was in a hurry, right? This is a vector. This is a vector. Why would I make this a scalar? I feel bad. I should basically say, whatever. I'll show you what I did down here. Let's see. Where did I, somewhere. Okay, boring. Some graphing. But now look at this. This equation is essentially a rewriting of alpha equals d omega dt, right? It's some variation on that. This equation is a rewriting of omega equals d theta dt, and then you just cross multiply. We're using all of the stuff in there. And then this just says change theta by a small amount. This is how you rotate things, Here's my updated, right? After I figure this out, I can get the new rotation vectors. And after that, I can then recalculate all this boring stuff, redraw all these arrows, and make a plot. So that's all that's going on here. Great. For another fun one, let's look at this one. I thought this is kind of interesting. I had a student work on this one. We could do different paths here, and in particular, let's do a polynomial, right? And now what I'm going to do here, when I run this thing, let's just look at it. It looks really complicated, right? What is going on there? Let's run this again. Let's see if I can reset. Oops. And I'm going to go back up to here. So in this one, I don't think do I have a sim speed? Where is it? Where's that? Oh yes, thank you. I'm going to slow this down. Thanks. When I run this thing, that big line that you see there, if you watch it, that's actually a circle. That's showing the radius of circular motion at any one instant. Notice that big arrow there was AC. Watch the circular radius. It's going to flip, right? Now it forms circular motion this way, and this is actually circular motion. Think about it. I know what you, right? This does not look like an object going in a circle, but at any one instant, you can treat the motion as circular. That's why what we're talking about right now is so fundamental. As you get to more complicated motion, you can model any motion in the universe as circular motion, except there's going to be V tan plus V radial. And we aren't going to do that in our class, but if you really understand this, you could model motion in polar coordinates instead of just X, Y, Z. Is that enough on the pretty pictures? Any questions about that? All right. If you're curious about that, you could look at it later. It's kind of a doozy of a code. All right. Let's stop that. Let's get back, and while I'm getting the board organized, why don't you read 10.3? Okay, 10.3. I hope that was a worthwhile expenditure of time. I need to do this. This. I think it's neat. Before we do this problem, you guys like that when I show you codes and simulations, or is that a waste of time? I mean, some people that are CS probably like it, right? Okay, so not everybody, maybe not for everybody, but hopefully at least some people get a reason to care. So if that works for me. What did I say, 10.3? Oh, boy. What's gonna happen here? Got a fly wheel. Gonna rotate. I'm gonna assume that up is K hat. I don't know why. It shows it. It doesn't really matter. Okay. We got this plot here. Two, four, whoops. I think omega was in units of radians per second, wasn't it?
Yes.
And time was in units of seconds. And this was -5, 5, and 10. From 5 to -5 in 4 seconds. From 4 to 5, it's a constant. Then 6, it goes all the way up to 10, doesn't it?
On the wrong board.
What's that? Oh, thank you, thank you. Oh, okay, there we go. And then from there, it goes down to 5 in the last 2 seconds, right? Is that kind of the
No.
graph?
No, not like that.
No?
From
Oh,
five-
shoot. Oh, I was wrong. Thank you for correcting me. So it goes up to here, right to there, and then it goes up to 10. Is that right?
Yes.
Thank you. Okay, so that's omega. All right, let's read part A. Oh, and we've got the radius. And there's a point mass superglued here. So this mass is 15 grams. And the radius is 0.20 meters. Let's not worry about sig figs on this problem. It says assume beta initial equals 0. Anything else in the problem statement that might be useful? That's it. Okay. All right. How would we figure that out? At what time does the mass return to its initial position? What do you think? Why do you say 6 seconds? That's omega. That's when it goes to its initial rotation rate. That's not its initial position. And that's a big hint there. So it's not when omega takes the same value, but instead when what? Yeah, yeah. Remember graphs? If area under curve, what is the area under the curve? true, but what's the area under, okay, let's go back a step. What's the area under a VT curve? Displacement. So what's the area under an omega t curve? Angular displacement. Don't overthink it. VT goes to delta x, omega t goes to delta theta. Did that make any sense? The area under omega t is angular displacement. So what this is saying is, when is angular displacement 0? We need the same amount of positive and negative area. When does that occur? 4 seconds. So this would be, what is area 1? Give me the units and the size of it. What's the area of that triangle? 5 radians. Excellent. Because the seconds cancels the per second. Outstanding. 1/2 5 radians per second times 2 seconds. Nice job. Notice what's area 2? -5, because it's below. Excellent. You guys are pretty good. This is twice, I don't know. You could say this. I've been torturing you all semester long, and lab's been tough. But you guys are performing at a high level. The earlier class did as well. I'm excited for you guys. I don't know if I'm too hard, probably, but you guys are learning your shit. So I'm impressed. Keep it up. The fact that you recognize it should be an area is very good. Okay. All right. Part B. How far, and do you agree that's good? You could probably find another time when it's the initial, but I only care about the first one, right? Because there's going to be another time when this equals that area, right? So you could find it again and again. All right. B. How far is the mass traveled? What do you think I'm asking for? Because if you can figure out what I'm asking about, usually you get it right. Right? It's not the math that's hard, it's the word problemness. How far? What does that mean to you? What's that? Okay, so some sort of absolute value, total distance. I like what you said. What are the units of distance? Meters. So what am I trying to find? Is this thing traveling the X direction, the Y direction, the Z direction, or something else? Which direction is the mass moving, or what would be a good name to describe the path traveled by the mass? Arc length. Right? It's spinning around. So we know that S equals R delta theta. But we're going to have to get S1 and delta theta 1, right? We could get S2. Let me draw this in just a second. We basically could get and I'm going to get lazy. Do you agree you could somehow figure out the area of that weird ass shape? Just triangle and a trapeze. That's just ugly, but. S4 would be that area. S3 would relate, oh, and I guess this is the area, right? Remember doing this in lecture in lab? And then because some of them are positive and some of them are negative, we got to get the absolute value. So then S total or distance, I'll get out of the way, give me a second. Distance traveled would be the absolute value of S1, plus the absolute value of S2, plus the absolute value of S3, plus the absolute value of S4. Pretty boring, right? More important than doing the problem is making sure you identify when I say these words, this is what he means, right? That's what you need. You guys are pretty good at algebra. You do not need to practice that as much. We need to practice what do I mean with these questions. Okay, part C. I'll get over here. For this one, I'm going to do this. How would we do part C? What are we plotting? A tan? Or no, alpha or what? What the hell? Alpha. How do you get alpha from a plot of omega? Slope. How do you know that? Alpha equals the omega dt. That's slope of omega versus t. Right? What do you think? Is this stuff not too bad, or I tried to destroy you in chapter 2 so that you could get this part easy, and I hope that's helping, but if I failed, I apologize. Let's sketch it. One, two, three, 4, 5, 6, 7, 8, 2, 4, 6, 8, t seconds. What are the units for alpha? Second squared. Yes, good. I'm just going to go like this. I have no idea. I think this will get the job done, but I'm not sure. Apologies if it's not perfectly symmetric here. Probably could draw it a little bit more perfect, but I didn't. Okay. Initially, what's alpha? Over here, what's the initial value of alpha? What's that slope? It goes down 10 in how much time? 4, what's that value? Negative 2.5. Does that make sense? The initial slope is negative 2.5 and it lasts until 4 seconds. What's the slope from 4 to 5 seconds? What's the slope from 4 to 5? Yeah. 0. Then what? Ooh. From -5 to 5 in 1 second is what? Ten. Because it changes 10 units. Does it do that for 1 second? And then the last one, it goes from 5 to 10 in 2 seconds. That's what? 2.5. Does that make sense? So I got this plot from these slopes. And now I'm going to get the right whiteboard so they can see better online. I got these from the slopes. How would you plot A tan versus T? Here's a hint. What's an equation that relates A tan to one of these parameters? What's an equation we know for A tan? R alpha. R omega is V. So R alpha, if we wanted to get A tan equals R alpha, what could we do? We multiply this plot by a radius and we're done. Does that make sense? And when you multiply by radius, you get a meters and you get meters per second squared. Piece of cake. Let's not even do it. Part E. How would you get this? What if we wanted to sketch AC versus time? What up, Dom?
Or omega squared.
Exactly. We know that AC equals R omega squared. So we wouldn't use this plot. We would use the original plot in the problem statement, square it. What happens when you square the plot to the numbers? In particular, what happens when you square negative numbers? It becomes positive. So the AC would become a magnitude, right? And we'd have all the negatives. So it's going to be complicated looking. But if I could, right, if you square this, this would be 25, that would be 0, this would be also 25, 25, 0, 25, 100. And then you'd have to multiply that by the radius. Ugh. Did that make any sense? Square each of these numbers, multiply by the radius. All right. Let's go back to here. Maybe I'll go here. Give me a sec. Okay, so now I have a question. In theory, you could make this plot. My question to you now is, even without making it, I think we can answer the next question, but it's tricky. When is the acceleration of the mass 0? So part F. When is the acceleration of the mass going to be 0? When I say acceleration, if I don't make any further clarifications, what do you think I mean by acceleration? It's okay to be wrong. Take a guess. A total. What was the equation for A total? It was that. Getting towards the end, you're tired. That's A total. Do you agree? This is AC squared plus A tan squared. Remember that?
The camera shifted more to the right.
Oh, shoot. Thank you. Is that better?
Yeah.
Okay. So that's what we need. So let's start out. Well, we've got alpha on this board. Let's look at it. At what time does this term equal 0? Four to 5 seconds, agreed? So the only possible time that this could be 0 is between 4 and 5 seconds as far as this term is concerned. So all we need to do is go over there and look at the omega plot and see when omega equals 0 between 4 and 5 seconds. Let's go look. Is omega equal to 0 between 4 and 5 seconds? No. So what is the correct answer to the question asked? Doesn't occur. You agree? In this particular one, this mass is always accelerating. Right? At instance when omega is 0, alpha is not 0. At instance when alpha is 0, omega is non-zero. You always have at least one component of acceleration. I think this kind of indicates why circular motion is so tricky. It's not enough just to say omega is 0, it's not accelerating. That doesn't work. It's not enough to say alpha is 0, it's not accelerating. Bad, bad, bad. Okay. Part G, I'm talking about the largest force. When I say largest force, what will we do? How would you get the largest force? Just remind me. What's the equation we used in the last problem? Which A? Yes, A total. So you'd have to take a little bit of time and figure out where A total is biggest. So you'd look at the graph, try a couple of numbers and see. Got it? Moving on. H. How do you get RPMs? In particular, let's go to the original plot. How do you get RPMs? Say again? Yeah, we got radians per second. How would you get RPMs?
Divided by 2 pi and multiplied by 1 minute.
Okay, yeah, because 2 pi radians is 1 revolution. 60 seconds would be 1 minute. Please, please, please remind me, approximately what factor will it change things by? What is this conversion factor approximately?
Times 10.
10. So it should be up to about 50 and down to about negative. Oh, wait, it goes, yeah, something 50, negative 50, 50, 100-ish. Agreed? What's the most common mistake students make? They forget to put parentheses around the 2 pi in the basement, and then they divide by 2, multiply by pi, and then they're off and they screwed up. So that's why that checking that factor is good. Should be off by about 10 either way. Good enough? 2 more. We can do this. 10.4. Lightning round. I'm going to erase this. 10.4. Any questions while I got it up? Okay, 10.4. We can do this. Like a review of chapter 2 in one day, huh? I'll let you skim it. enough. Get on with it. Whatever, close enough. 10.4 flywheel, always with the flywheels. X, Y, Z. What do we always check? X goes to Y, goes to Z, looking good. There's a disk here. All right, that's a terrible looking disk. Okay. Rotating. R equals 0.200 meters. We get some screwball equation here. Omega of t equals that. How do you find the units? Give me the units of 8. We should know the units of our constants before we trust them and start working with them. What does that have to be?
Per second squared.
That's correct. If it helps, remind me, what are the units of omega of t? What are the units of omega in general? Radians per second. The units of time are seconds. The only way this is going to work out is if this is radians per second squared. Similarly, what are the units of the negative 6.00?
Radian per second cube.
Yep. So now we know our units, even though they weren't explicitly stated. B. What unit vector is implied? Y hat or J hat. Yeah, J hat, Y hat. No, Y hat is oftentimes used. That's fine. Yeah. Y hat or J hat, however you want to call it. Either way is fine. If you're an engineer, sometimes they'll use E sub Y, but I can't help it if they're crazy. Sorry, Dom. Yeah, you don't use that? Oh, you use E sub R and E sub theta? Yeah, okay, my bad, my bad. Not for this problem, not for this problem. Even engineers aren't crazy. All right. Let's see. Determine revolutions. Let's go to part C. Revolutions completed by wheel when it has max rotation rate in positive direction. All right, how would we approach that? Let's break it down one piece at a time. Revolutions completed. What does that mean? What are revolutions completed? What symbol might that mean? Not the period. Not the frequency. Revolutions. What is a revolution of something? A circle, yeah. So what's a name for going around in a circle? For a variable name.
S.
S would be arc length for a point on the rim. Revolution is thus not quite delta theta. Theta is, right? If you know how many radians, isn't that how many revolutions? Isn't that how much theta? Revolutions, radians, theta. All right. What's the max rotation rate piece? I want the max what? Maximum time, maximum frequency. What? Well, what do you want here? If I'm talking about maximum rotation rate, we want max omega. How do you get the maximum omega? How do I get the maximum omega? Calc class. Calc class. Excellent. You guys are tired. D omega dt. Set it equal to 0. Solve for t. Then we could take that time and we should probably do a second derivative test. Do you remember that? To make sure it's a max. Good. Okay, so wait a minute. Why can't I just use my normal equations? Like, why can't I use this? Delta theta equals omega initial t plus 1/2 alpha t squared. Why don't I just do that? This is a rotational kinematics equation. My claim is this is not true anymore. Why not? When does this apply? Constant alpha. Is alpha a constant? How do you get alpha? What is alpha? Which is? Right? Is that a constant? This is not constant, therefore this does not apply. Can't use it. Got it? That's what I'm saying. Is it coming back? Chapter 2? All right, all right. So this is this problem 10.4, and just so we get a hint here, well, let's I'll let you look more at the rest of it. Let's look briefly at 10.5. That's the last one that I wanted to get through. We'll just introduce it and see if you recognize the problem. We got 2 minutes. What are we told here? Initial rotation rate omega naught slows down according to rate alpha equals K is a positive constant. Determine, am I on the right whiteboard? Yes. Any ideas what we do? Yeah. Tell me what I should write for the integral. Like, what would you write on your paper? K omega squared times, or yeah. Huh. And then you integrate that. Why is that difficult? Omega is some function of time, but do you know the function of time? So we don't have anything to plug. That's what we're trying to figure out. That's not going to work. It's time to go, so I'll just tell you. Separate before you integrate. Remember that? This is the separation of variables. You remember when we did that? There's something wrong with what I wrote here. It's subtle. We're tired. I'm just going to tell you. It comes from this word slows down. So that means we need to stick a minus sign in there. All right, good enough? I'll tell you the same thing I told the other class. We were up in Cal Poly the other day, and we were talking with the mechanical engineering instructor. He says he gives a problem very similar to this for the, remember the hockey puck sticking to the edge, spinning around the gravitron? He's like, how many revolutions pass before it falls down if we assume this is true? So just letting you know, I'm not the only person that's crazy and does this separation of variable junk. All right, is that good? Stopping the live stream. Oh my goodness.